And we're back. Today we're going to talk about, once again, free energy and entropy in chemical reactions. And we're going to do that by looking over a couple of examples. So let's say we have the following reaction. So gas A2, diatomic molecule, reacts with gas B2, another diatomic molecule, to produce gas AB. So that means in order to balance this equation, we need to add a coefficient of 2 in front of AB. And we want to predict the signs of each of the following. So first off, for delta H, it says in the question, the bond energy of AB is much greater than that of either reactant. So since the bond energy of the product side, AB, is greater than the average bond energies of the reaction, this reaction is exothermic, making delta H negative. Then, since this reaction is exothermic, since it's releasing heat to the atmosphere, to the surroundings, that means the change in entropy of the surroundings is positive. It's increasing the motion, the relative motion of the particles surrounding them. Then, since here we have two molecules of gases in our reactant side, one molecule of A2, one molecule of B2, and then two molecules on our product side, we would expect the change in entropy of the system to be 0 or very close to 0. So we say it's around or almost 0. So that means for the total entropy of the universe, if we have positive and we're adding 0, that means the change in entropy of the universe has to be positive. So you should be able to analyze a reaction like this and determine the signs of each. Even if you're not given any numerical data, you should be able to predict these signs. Okay, and with the following, with entropy here, you should be able to interpret this for the third law of thermodynamics. So first off, the entropy of a perfect crystal at 0 Kelvin, so that's absolute 0, so the entropy of that is 0. The reason for that is that molecular motion completely stops. Okay, that means those particles are not moving at all. And in general, the entropy of a substance increases with temperature. And the reason for that, at a higher temperature, those molecules are moving faster and faster, therefore they have more randomness and more disorder. And one other point I want to make is that usually for larger molecules, the change in entropy, or entropy, will be larger since they have more possibilities. They have more possible rotational and vibrational motions. And if you remember from last class, the more molecules we have, if we have more molecules in the product side, that means delta S is positive since there are more possible configurations. There's more disorder and more potential disorder. Okay, so entropy is proportional to temperature. As you increase the temperature, entropy will also increase. And entropy is also a state function, meaning it is independent of pathway, and it is an extensive property. So just like the change in enthalpy, so it's a state function, extensive, and similar to enthalpy. So that means when we're at standard conditions, remember this degree sign represents standard conditions, 25 degrees Celsius and 1 atmosphere of pressure. Now we can, just like the equation for delta H, we can use the entropy of the products minus the entropy of the reactants to determine the overall change in entropy of a reaction. And just like all those values for delta H were in Appendix 4, the same values are there for delta S in Appendix 4, or they will be given to you in a problem like so. And the main difference I want to point out is delta H for those elements that were in their standard form at room temperature and pressure. That is no longer the case for entropy. So these are not zero like delta H. And if you think about it, that makes sense. Even sodium is a solid. It doesn't have very much entropy. The molecules themselves are not moving around very much. However, it's still more than zero. So using that, the data like that, you should be able to calculate the change in entropy reaction using the products, and you have to look at the coefficient. So the first product, 2NaOH, we take 2 moles times the value for NaOH, which was 50 joules over mole times Kelvin. And here the moles cancel. So that means our final units here for the entropy change of the reaction will be in terms of joules per Kelvin. And we add that to the other product. So H2 is 131. And that'll be joules per Kelvin since you're multiplying just by 1 mole. And we subtract by now the two products. So there's 2 Na, so 2 times 2 moles times the value for Na, which is 51. And still here the units will end up joules per Kelvin. We add by the entropy of 2 moles of the H2O as a liquid. So that's 2 times 70, and the units there will end up joules per Kelvin. Okay, then once you do all that, you get a value of negative 11 joules per Kelvin. And so that means that the entropy is decreasing. And that makes sense for this reaction because we start out with a solid and liquid, and we are going to an aqueous and a gas. However, here we have a total 2 plus 2, 4 molecules on the left side, the reactant side, and 2 and 1, 3 on the right side. So those two contradict themselves. So you would expect, just by looking at this reaction, delta S to be somewhat close to 0. So that's why it has a relatively low magnitude. Okay, so you should be able to calculate delta S for any reaction and predict its sign. Okay. And you should, just like we did for delta S, entropy, the same thing applies to free energy, delta G. It's also a state function and an extensive property, so the same exact equation applies. The products minus reactants, and it's just like delta H, delta S. All those values are in Appendix 4. And it is most similar to delta H because for these standard states, for the elements, the production of the elements, they're at equilibrium, they're in their natural form. So for elements, the delta G for all the metals is solid or diatomic gases, those values will be 0 for delta G. And remember, the Gibbs free energy, the delta G, determines if the reaction will occur. Remember, it's negative. If it's negative, it's spontaneous. So that means the more and more negative it is, the larger the magnitude of the negative number, the more likely the reaction will occur. Or if it's positive, the larger and larger magnitude, the harder it will be to occur. Okay, so here there's two different ways to calculate delta G. Normally this way, the way we did it last class, is easier if you're given delta H and delta S at a given temperature. However, sometimes you will not be given those, and in that case you have to use the values from Appendix 4 to calculate. You have the individual values of each of the products and reactants, and then from that you can calculate the delta G of the reaction. And so for a reaction like this, so let's say we have the production of ammonia. So we have that. And you should also be able to predict the value of delta G. So we know here, in this case, if we're trying to predict the sign of delta S, you have one molecule here, 3 here, so 4 molecules of gas on the left side, 2 on the right side. So that means the entropy is decreasing. So you would predict the entropy there would be negative. And here, this reaction is exothermic. So that means the delta H value is negative. And if you were given actual values here for delta S and delta H, you should be able to calculate the numerical value for delta G. Because in this case, since both of these are negative, you're unsure if delta G will be negative. It's dependent upon the magnitudes of both delta H and delta S. Okay, so you should be able to use either of these equations to solve for delta G of a reaction. Okay, now, finally, if given a reaction like so, a stable diatomic molecule spontaneously forms from its atoms. So, let's use hydrogen as an example. So, it's forming, so that means it's a product from its atoms. So H2, hydrogen, comes from 2 hydrogen atoms. And we want to predict each of these signs. So first off, if we look, we start with 2 molecules of gas here, only 1 here. So that means our entropy is decreasing, so that's negative. And here we're combining 2 separate atoms. So that means energy is released. That reaction is exothermic. That makes delta H negative. And then if both of these are negative, now we can definitively predict the sign of delta G. So if both of those are negative, so both of those are negative, so it's dependent upon the temperature. However, in this question, it says the molecule spontaneously forms from its atoms, so that makes delta G negative. And here, once again, if you're given values of delta H and delta S, you should be able to calculate for delta G, or if you're not given those, you should be able to use Appendix 4 to calculate the delta G value for this reaction. And same thing using this equation. If instead you're given the delta G of a reaction and not given one of the products or one of the reactants, you should be able to work backwards and solve for x, or solve for that unknown. All right, that's all for today. See you next time.